Welcome back to the Stiffness Method. In this session, we'll expand on what we did in the previous session, finding reactions and internal forces in trusses, to beams and frames. We'll have a quick recap of the theory, solve a frame example, and then move on to coding. So far, we've used the stiffness method to build and solve the equation KD equals F, giving us the displacements of every node in the structure. We've also calculated support reactions and internal forces carried by each element in a truss. We will now move on to completing exactly the same procedure, but in a frame. We'll recap and discuss the theory, we'll solve an example, and then we'll move on to programming the whole process. Let's begin once again with the core of the stiffness method, the global equation KD equals F. This relationship connects the global stiffness K, nodal displacements D, and the external load vector F. Every analysis using the stiffness method starts from this equation. Once assembled, we can partition it to separate the free and restrained degrees of freedom, which will be our next step. As we've shown before when we discussed trusses, we can now partition the global stiffness equation into submatrices that represent the interactions between restrained and free degrees of freedom. This gives us 4 blocks: KRR, KRF, KFR, and KFF. Partitioning allows us to isolate the reduced system, containing only the free displacements, which we can then solve using the loads applied at those degrees of freedom. The reactions can later be recovered from the full equation. We already demonstrated this in the previous session, but as a quick recap, we can cross out the restrained degrees of freedom with red lines, which allows us to clearly see the restricted and free areas. The red boxes highlight the members of KRR, the restricted members. The orange boxes highlight KFF. This block is the most important one because it contains the portion of the stiffness matrix that we will use in the main reduced equation KFF multiplied by DF equals FF. The purple boxes highlight the members of KRF and the grey boxes highlight KFR. Altogether, these 4 coloured blocks represent the fully partitioned global stiffness matrix for the frame. Once boundary conditions are applied, only the KFF portion is used to find displacements, and the other submatrices are used afterwards to recover the reactions and verify equilibrium. When we partition the global stiffness matrix, its rows and columns are grouped according to restrained and free degrees of freedom. The number of restrained degrees of freedom is NR, and the number of free degrees of freedom is NF. The 4 submatrices KRR, KRF, KFR, and KFF follow directly from that count. Now that we've partitioned the global system, let's focus on the restrained rows. These correspond to the supports. From the original global equation, we can express the restrained degrees of freedom, the supports, in terms of known displacements, which are usually 0, and the computed free displacements. Substituting these into the partition form gives us the reaction equation R equals KRR times dR plus KRF times dF minus FR. As we've already discussed previously, if the supports don't move and no load acts directly on them, the formula reduces neatly to R equals KRF times dF. And that's the version you'll see most often, and is the one we'll use in our frame example. And finally, to evaluate the internal forces in each element, we'll start with the reduced matrix equation F tag equals K times D tag. F tag is the local end force vector, K is the element stiffness matrix, and D tag is the end displacement vector expressed in the element's local axis system. From previous lectures, we also established that local displacements can be obtained from the global displacements that we found using the transformation matrix T, so that D tag equals T times D. By substituting this into the first equation, we get the relationship F tag equals K times T times D. This expression directly links the global displacement vector to the local internal forces in each member, showing how the stiffness method allows us to recover member-level results from the overall structural solution. It's very important to stress here that the results from this are the end forces. So that will mean the end axial, shear, and moment of the element. So if we have a UDL, it will not give us the moments or forces in the element, only the forces and moments at the ends of the element. That means that if we want the forces and moment at some place in the middle, we need to create a node there, or we need to figure it out from different types of solutions after we have the end moments and forces. Before we start solving a frame example, let's quickly summarize the full procedure. Once we've solved KD equals F and know all the nodal displacements, we're ready for the two final steps. Step 1, we recover the reactions at the supports using the restrained part of the stiffness equation, and that gives us the forces each support must provide to keep the structure in balance. Step 2, we then find the internal forces in each element. We extract the nodal displacements, transform them into the local coordinate system using the transformation vector, and multiply by the local stiffness matrix K. This gives us the axial or bending forces within the element. We can then check global equilibrium or plot diagrams and rotate everything back using the transpose of the transformation matrix. And finally, we confirm that the element and forces are equal and opposite, and the total reactions and nodes balance. A good numerical check that everything is consistent. And this is the process we'll follow now, step by step, for our frame. So, let's now apply the full stiffness method procedure to our two-column portal frame example. The beam carries a uniformly distributed load of 10 kN per meter and a 20 kN point load acting downwards at node 3. In addition, I have added a horizontal force of 15 kN at node 2. This lateral load allows us to explore how the frame resists combined bending and axial effects, giving a more complete picture of the behaviour. At the base, the frame has a pin support at node 1 on the left and a roller at node 4 on the right. And this means that this structure is determinant, and we can solve it as well by hand to check everything that we've done here. Each member, both the columns and the beam, have a square cross-section of 200 millimeters and an elastic modulus of 200 gigapascals. We've already assembled the global stiffness matrix for this from earlier sessions, and we can quickly amend the load vector before solving the reduced stiffness equation KFF times DF equals FF to obtain the nodal displacements. So this is the full system before we reduce it. The only thing I need to do here is update the load vector. So in early examples, we only had vertical loads, the uniformly distributed load on the beam and the point load at node 3. Now that we've introduced this 15 kN horizontal load at node 2, it must be added to the corresponding degree of freedom for the horizontal translation at node 2, highlighted in red. That modification ensures that the load vector correctly represents the vertical and horizontal actions on the frame. Next, we apply support conditions to reduce the global stiffness system. By removing the restrained degrees of freedom, rows and columns for degrees of freedom 1, 2, and 11, we obtain a reduced matrix containing 9 equations for 9 unknowns. This reduced form retains the essential structural behaviour while enforcing the physical boundary conditions at the supports. We can now see the reduced force vector FF, the reduced submatrix KFF, and the 9 degrees of freedom. After applying supports and loads, we arrived at the reduced stiffness system KFF times DF equals FF, which contains the 9 degrees of freedom. Solving this system gives us the displacements and rotations of the unconstrained nodes. Once dF is known, we can rebuild the full global displacement vector D. The solved free displacements are inserted into their correct global positions, and the restrained degrees of freedom are set to 0. This ensures that every node is represented in global coordinates and prepares us to compute support reactions and internal forces next. Once the free displacements have been determined, the reactions and the restrained degrees of freedom can be recovered directly from the partitioned form of the global equilibrium equation. The reaction vector R represents the additional forces that act at the supports to maintain the prescribed boundary conditions. As we know from before, when the support displacements are 0 and there are no external forces on the restraint, this simplifies us to the familiar result R equals KRF times DF. This is typical in standard textbooks for recovering reactions in the stiffness method. Now that we've solved for the nodal displacements, we can recover the support reactions using the reaction equation R equals KRF times DF. In this example, the submatrix KRF represents the coupling between the restrained degrees of freedom and the free displacements. By multiplying this matrix by the displacement vector dF, we obtain the corresponding reaction forces at the supports. The calculated results are shown here. The horizontal reaction at node 1 is minus 15 kilonewtons acting to resist the applied 15 horizontal load. The vertical reaction at node 1 is 22.5 kilonewtons, balancing part of the vertical loads. And the vertical reaction at node 4 is 57.5 kilonewtons, completing the equilibrium for the frame. The results confirm that the structure is behaving consistently with the applied loading. We've already used the transformation matrix T earlier to convert each element's stiffness matrix from local coordinates into the global system. Now we'll use the same transformation matrix, but in the opposite direction, to transform the global nodal displacements back into local element displacements. Once we have these local displacements, we can multiply them by the local stiffness matrix K to obtain the member end forces in the element's local coordinate system. K is the element stiffness matrix in local axes, and T is the transformation vector that contains the cosine and sine terms that describes the member's orientation into the global system. This expression allows us to calculate axial forces, shear forces, and bending moments in each member, completing the link between the global displacements and internal actions within the structure. Let's apply this transformation to member 1, which connects node 1 and node 2. The transformation matrix T1 defines the orientation of this member. In this case, it's vertical, so the transformation involves simple sign changes between the local and global coordinate systems. Next, we substitute the local stiffness matrix K1, and that contains the member stiffness coefficients and the global displacement vector D1, representing the nodal displacements and rotations at nodes 1 and 2. Combining these terms, we can calculate the local end forces for this member. This step translates the global displacement results into the element's local coordinate system, ready for evaluating axial, shear, and moment actions. After performing the multiplication, we obtain the local end force vector for member 1. These values correspond to the internal axial forces, shear forces, and bending moments at each end of the member. I'm first showing how the orange arrows, which are the arrows in the directions that we've assumed the forces are, before moving on to, at the right-hand side, transforming everything into their real direction. So where there was a minus, for example, the axial force at node 2, I've put the arrow in the correct direction. So I've taken into account the fact that it was negative and changed the arrow to respect that. It means, for example, that once applied in the correct directions, the axial force, for example, is demonstrating compression. The shear forces in purple act in opposite directions, maintaining equilibrium. The resulting bending moment of 45 kilonewton meters develops at the top of the column, showing how the frame resists the lateral action through bending in the vertical members. We can see in the red arrow that the tension is on the inside of the column or on the right. And this all confirms that our transformation and the stiffness formulations correctly reproduce the internal behavior of the frame element. Next, we'll apply the same procedure to member 2, which is the beam spanning between nodes 2 and 3. The transformation matrix T2 in this case is the identity matrix, since the beam lies horizontally. Its local and global axes are already aligned. We substitute the corresponding local stiffness matrix K2 and the global displacement vector D2, which contains the displacements and rotations at nodes 2 and 3. And using the same relationship, we can now compute the local end forces on this member. This allows us to evaluate how the beam resists both the vertical loading and the horizontal force transmitted from the column, producing bending moments and shear reactions along the length. Carrying out the calculations gives us the local end force vector for member 2. These values correspond to the shear forces and bending moments at each end of the beam. At node 2, the upward reaction is 22.5 kilonewtons with a 45 kilonewton meter moment, which is the opposite direction of our sign convention. So in this case, tension is on the bottom, which matches the result from member 1. At node 3, the upward shear is 37.5 kilonewtons, balancing the applied distributed load. There is no axial force along the beam and no moment at node 3. We can check and find that the beam is in static equilibrium. It's important to remember that the stiffness method provides the internal forces only at the member ends. The variation of bending moment or shear force along the beam, such as the parabolic shape we'd expect under the UDL, is not obtained directly from this analysis. To determine the internal distribution between nodes, we would use these end forces together with beam theory, for example, to construct the shear force and bending moment diagrams. We can check these results by hand or using a program visually to compare that the numerical outputs make physical sense. Altogether, this will confirm that our stiffness method solution is consistent, accurate, and physically realistic. And we'll finish with a short recap of the full stiffness method workflow. First, we assemble the global stiffness matrix K and the load vector F, combining the contribution of all elements in global coordinates. We then apply the boundary conditions, set the restrained displacements dr equals 0, remove the restrained degrees of freedom, and form the reduced system. We can solve that for free displacements df, and these define how the whole structure deforms. From there, we recover reactions, which for fixed and unloaded support simplifies to R equals KRF times df. We then compute the internal forces for each member by using F tag equals K times T times D, and finally we check equilibrium, making sure that the global and local forces balance. Once the displacements are known really, everything else, reactions, internal forces and stresses, will follow directly from this sequence. In the next part, we'll translate this workflow into code step by step in MATLAB or Octave so that the entire process from assembly to internal forces is fully automated. And now that we've established the full theoretical foundation, we'll move on to implementation. We'll translate this procedure into a short MATLAB or Octave script using the same frame example we've just analysed. As I've mentioned before, the aim here isn't to turn into programmers, but to show how each theoretical step maps directly to a line of code, bridging the gap between structural theory and computational practice. This will be a quick look at the coding process, focusing on the final stage, solving the stiffness equation and obtaining the displacements, reactions, and internal forces. If you'd like some more detail for the previous steps, you can revisit earlier coding sessions where we built up the framework step by step. We start off, as always, by setting up a clean script using clear, close all, and CLC. The header reminds us this is a 2D frame using the stiffness method, and all inputs and outputs are in SI units, so forces in newtons, lengths in meters, and stiffness in newtons per meter. The next few slides will look familiar. We'll go through them briefly, and if you'd like a full recap, as I said, revisit the earlier lectures where we built these sections in detail. This section defines the input data for our frame example. We start by listing the node coordinates in meters and specifying that each node in the frame has 3 degrees of freedom: horizontal, vertical, and rotational. The element connectivity matrix tells the program which nodes are connected by each member. We then count how many nodes and elements are in the structure, and finally number the degrees of freedom automatically for each node. These identifiers will be later used to assemble the global stiffness matrix efficiently. And here we can see the degree of freedom numbering matrix N, showing how the degrees of freedom are assigned to each node. Next, we define the material and section properties for all members in the frame. The modulus of elasticity E is set to 200 gigapascals, typical for steel, and assigned uniformly to every element. The cross-sectional area A corresponds to a 200 by 200 millimeter square section converted to square meters. And finally, the second moment of area, I, is calculated for that same rectangular section and applied to each element. The function ones is used here to assign identical properties to all members, but this can easily be changed if required, for example by entering different E, A, or I values directly for each element. This part of the script calculates the geometry of each element based on the nodal coordinates. For each member, the program extracts the start and end nodes and then computes the differences in x and y, the member length, and the direction cosines, cos theta, and sine theta. These values define the orientation of each element in the structure and will later be used in the transformation matrix. The angle theta is also calculated using the a tan 2 function expressed in radians for all subsequent stiffness calculations. The results, including the element length and angles, are stored in arrays and displayed to confirm that the geometry has been processed correctly. This step computes the local stiffness matrix for each frame element. Each member has 6 degrees of freedom, 3 at each node, and the matrix combines axial and bending effects using EA and EI. The results are stored in K-local for all elements and can later be transformed into global coordinates and reused when recovering the internal member forces. Here we can see the matrix for element 2 as an example, confirming that it matches what we derived in the earlier theoretical session. In this step, we rotate each element's stiffness matrix from its local coordinate system into the global system. Using the cosine and sine values for each member, we build the transformation matrix T, which relates local and global displacements. The global element stiffness is then obtained using T transpose times K local times T. We compute and store both the T and KLM here. The T matrices will later be needed to find the internal member forces, and the KLM matrices are stored at this stage to assemble the full global stiffness matrix. Here we can see the transformation matrix for element 2 as an example, confirming that it matches exactly what we derived in the earlier part of this session. In this step, we assemble the global stiffness matrix K for the entire structure. Each element's stiffness matrix is added in the correct positions of K according to its connected degrees of freedom. This process combines the contributions from all members into one complete structural model. And here is the full global stiffness matrix, so we can verify that the assembly has been carried out correctly. Here we define the global load vector F for the structure. Two types of loading can be applied. A, concentrated nodal loads acting at the global x, y, and moment directions, and uniformly distributed loads, or UDLs, acting along the elements in their local y direction. In this example, a 15 kN horizontal load acts at node 2, and a 20 kN downward load acts at node 3. Element 2 also carries a 10 kN downward UDL, representing the roof load. The program includes safeguards so that if no loads are defined, the vectors remain empty. This short loop assembles the nodal loads into the correct entries of the global load vector F. For each load listed in the nodal load table, the code identifies the node and adds the corresponding horizontal, vertical, and moment components to the appropriate degrees of freedom, u, v, and theta. The result is a complete global load vector where all external forces and moments are positioned consistently with the structure's degree of freedom numbering. In this part of the script, we deal with the uniformly distributed loads on the elements. First, we create FE lock all, a container that will store the local fixed end forces for each element. This is a small addition compared with the previous version of the code and is later needed in step 9, where we calculate the internal member forces. For each UDL, the code reads the element index and load intensity WY, computes the corresponding local fixed end force vector FE loc for a prismatic beam under uniform load, and accumulates these in FE loc all, and uses the elements transformation matrix TLM to rotate FE loc into global forces FE globe, which are then assembled into the global load vector F. So in this step, we both include the effect of UDLs F and store their fixed end forces ready to be used later when finding the element internal forces. And here we can see the full load vector, which includes both nodal and uniformly distributed loads, exactly as we expected. And now we're ready to solve the stiffness equation to find the nodal displacements. We start by defining the support conditions. In this example, node 1 is pinned, so U1 and V1 equal 0, and node 4 is a roller, with V4 equaling 0. So we can see this here in the fixed offs, the first line of code, N11, so node 1, direction of degree of freedom 1, N12, so again, node 1, direction of degree of freedom 2, and node 4, 2, so node 4, degree of freedom 2, or V. The program then separates all the degrees of freedom into restrained and free sets, and using only the free degrees of freedom, we can form the reduced stiffness equation KFF times DF equals FF, and solve for the unknown displacements DF. Finally, we reconstruct the full displacement vector, setting the restrained values to 0. At this point, we have the complete displacement solution for every node in the structure. With the nodal displacements known, we can now calculate the support reactions. Using the full stiffness equation R equals Kd minus F, the program computes the reaction forces and moments at all degrees of freedom. These appear only at the restrained degrees of freedom which correspond to the supports, which we can then extract into R support, giving the complete set of support reactions for the frame, as we can see on the slide. In this step, we calculate the internal forces in each frame element expressed in the local coordinate system. For every element, the program first gathers the nodal displacements from the global displacement vector and converts them into local displacements using the stored transformation matrix TLM. Multiplying these by the local stiffness matrix K local, gives the element end forces that would arise if the member was loaded only through its nodal displacements. However, since our elements may also carry uniformly distributed loads, we already included those in the global load vector. Those UDLs create their own fixed end forces in the local system, which we stored earlier in F loc all. To avoid double counting, we now subtract F0 equals Fe loc all from the stiffness-based forces. This correction ensures that the final internal forces reflect the combined effect of all external and distributed loads without duplication. The resulting local force vector contains 6 values, 3 at each end of the element, representing the axial force, the shear force, and bending moment at the start and end nodes. These are the complete internal actions for every member, fully consistent with the structure's geometry, loads, and support conditions. At this stage, the analysis is complete. Every quantity in the stiffness method process is now known. Step 10 simply reports the results so that we can interpret and verify them. First, the program displays the global stiffness matrix K, followed by the element lengths and angles, confirming that the geometry and connectivity has been assembled correctly. It then prints the global load vector F and the nodal displacement vector D, which contains the translations and rotations at each degree of freedom. Next come the support reactions. These are the forces and moments acting on the structure at the restrained degrees of freedom. And finally, the script lists the element end forces in local coordinates. For each member, the output gives 6 components: axial force Fx, shear force Fy, and bending moment M at both the start and end nodes. These values allow us to interpret the internal actions throughout the frame and to draw the shear force and bending moment diagrams if required. And with this, the analysis is fully resolved, from input data and assembly to displacements, reactions, and internal forces, completing the full stiffness method workflow. And here we can see the numerical output from our MATLAB solution. At the top are the support reactions, horizontal and vertical forces, and moment restrained at the restrained degrees of freedom. In this case, the pin support at 1 and the roller support at 4 provide the required restraints to keep the frame in equilibrium under the applied loads. Below, the table lists the element end forces in local coordinates. Each row corresponds to a member, giving the axial force, shear force, and bending moments at both the start and end nodes. If you compare these with the results that we've previously come up with, you may notice some very small numerical differences. This is perfectly normal. MATLAB retains many more significant figures, while manual calculations often introduce small rounding errors at each step. And with that, we've completed the full frame stiffness method solution. And as always, although we've shown this code in MATLAB, it'll also run directly in Octave, which is a free open source alternative. It uses almost exactly the same syntax as MATLAB, so you can copy and paste this script and it should work without any changes. And just like that, we've reached the end of the stiffness method. We've gone through the full theory for both truss elements and beam and frame elements. We've also coded the full process into a usable code, one for trusses and one for beams and frames. And that's it. I will add on some more examples and perhaps a bit of code tweaking just to show things like putting all the input in one block in the beginning, just for ease of navigating through the script. But that's it. You have all the tools to solve any structure using the stiffness method. Enjoy!